Okay, good morning. Yesterday we started talking about electric field in circuits, and we saw that to keep a continuous and uniform stream of electrons flowing in a circuit, we needed an electric field because the electrons kept losing energy by colliding with the atomic lattice in the metal, the vibrating atoms, metal atoms. And that electric field was, we hypothesized, due to, or we reasoned really, due to charges that were both on the ends of the battery and that built up on the surface of the wire. And I'd like to just explore that a little bit more with you today. Our two topics for today are to explore that a little bit more and then to talk about energy in circuits and to actually see how using things we already know, the definition of steady state, sort of AKA the current node rule, and what we know about energy conservation framed in terms of potential differences, namely that the delta V for a round trip path has to be 0. We can actually calculate how big the electric field needs to be, not only in a simple circuit, but in a more complicated circuit, different parts of a more complicated circuit. So that's the agenda for today. So last time, we talked about a kind of a model circuit that looked like this, where the wires are drawn as thick wires, so we can talk about what's going on inside the wire. And presumably this is a wire that isn't a great conductor, so you need a significant electric field to do that. And we used a mechanical battery because it was actually easier to understand than chemical battery, at least for a physicist. And so the idea was that in the battery, charge built up on the ends of the battery, which are in fact labeled plus and minus, and that we could sort of model this. We could make a battery actually that was made of plates like capacitor plates. And the idea is that in order to keep the charge on those plates the same, even though electrons are flowing off this plate and onto that plate, we would have to transport electrons from the positive plate to the negative plate. And to do that, we'd have to do some work. We'd have to turn a crank or use a conveyor belt or something. So we'd have to put energy into the system. And that's part of what we'll explore today. And we found that, though, that those charges didn't make a field that would actually give us a steady state current. It made an electric field that varied around the circuit, and therefore we wouldn't get the same current everywhere, and that would not be a steady state because we'd have charge building up in some places and disappearing for other places. And by thinking through it step by step, we came to the conclusion that in order to get something that really would look like a steady state, we need to have not only the charges on the battery, but also some charges on the surface of the wire in some sort of complicated pattern in this case that would also contribute to the net electric field inside the wires. So we'd have, we first reasoned about these bends here where it was easy to see that we'd end up with a deficiency of electrons here initially and an excess here. But in fact, charge would build up all over the wire to give us, until we got the pattern of field that we actually really needed. Now this is pretty complicated, and so the question is, how do we figure out? And there are two questions: why does that work, and how do we figure out what happens? So it's actually a little bit, so what I'd like to show you are two things. I'd like to show you a VPython program that actually calculates basically from first principles from the Coulomb interaction, the idea of electric forces, how charge would build up on the surface of a circuit, the exact pattern, and then a discussion of kind of why that works, also in VPython. So here's the first. So here's the first piece of that. So here are a collection of rings of charge. You may remember that we've calculated the electric field due to a ring. We found an algebraic solution for the field along the axis, but in order to get the field at places that weren't right on the axis, we'd have to do it numerically. And so here is a collection of charged rings. The red rings are positive, the ones that are slightly blue are slightly negative, and a ring that's white has 0 net charge on it. And so a slightly pink ring is a little bit positive and whatnot. So what we've got here is what's called a gradient. Remember, a gradient is just a spatial derivative. So a situation in which the amount of charge varies with location. And so let's think about, before we actually look at this, let's try to figure out what the electric field inside these rings. Imagine that these rings of charge are coating a cylinder like a wire, for example, and figure out what the electric field due to these rings of charge would actually be. So let's think about that for a minute. Okay, so here is a question. Suppose we had a wire whose surface was coated with charge, and we're sampling, so here's a wire, okay? And there's charge all over the surface of this wire, and we're just sampling here at intervals to show what the charge is. It's indicative of the charge distribution on the whole wire. And these are all positive, and they're actually all have the same amount of positive charge. So this is uniformly positively charged. So we're interested here in location A, which is in the center of this wire, and we've got 5 positively charged rings to the right of it and 5 equally positively charged rings to the left of it. And the question is, what would be the direction of the net electric field due to all of those rings at location A? Okay, looks like most of you have answered. And you said that the net electric field would actually be 0 there. And that's right. Because for every ring to the right of location A making electric field that way, there's a ring an equal distance away making electric field that way, and so the net electric field would add up to 0 there. So that's exactly correct. What if, though, we had a gradient of charge here where blue is negative, red is positive, and the gray ones are practically neutral. Okay, what would the net electric field at location A now be? The direction. So you said the direction would be 7 to the left. And that also looks correct. Because at location A, these positive rings make an electric field to the left, and the negative rings also make an electric field to the left, so the net electric field would be to the left. So if we have this variation in charge, then we can get a net electric field in one direction. But does it actually have to be just positive and negative, or could it be some other variation in charge? So let's think about a case where a situation in which these charges, so the rings at the left are very red, so they have a lot of positive charge here. So that's a lot of positive charges here. And then there's a little bit less and a little bit less I'm sorry, at the right here. So we start at the right. This ring has lots of positive charge. And as we go to the left, it has a little bit less and a little bit less and a little bit less. And you can see that the rings are getting paler, and a little bit less here and less here, and actually neutral here. So the amount of charge gradually decreases. What would that do to the electric field at location A? So here's what you said. You said the electric field at location A would still be to the left in this case, even though there aren't any negative charges around. And that's a key insight, and it's exactly correct. So because these rings on the left have more charge, and the rings on the right, I've got left and right backwards today. The rings on the right have more charge, the rings on the left have less charge. Even though the rings on the left, if you add up all their contributions, they would make an electric field to the left, the rings on the right, which are the same distance away but have a lot more charge, would actually make the rings from the right side make a field to the left, the rings from the left side make a field to the right. So we definitely get a net field this way. And that's kind of the key insight we need to understand how charge on the surface of wires can make an electric field inside the wires that actually is uniform, which it has to be to drive a uniform current, and in the appropriate direction. So now let's look at this VPython program, which actually does that calculation for us. Okay, so here's a program in which we have a whole bunch of rings of charge, like the charge coating the surface of a wire in a circuit. And the little bumps are the point charges. So what we're doing in order to calculate the field, we want to calculate the field of a ring, not just on on the midline, but everywhere in, whoops, let's try this again. Everywhere inside this cylinder, the wire. And so what we're doing is we're approximating modeling each ring as a collection of point charges, just arranged in a circle, like we did analytically. And then we're just, with Python, looping through and adding up at every observation location, adding up the contribution of all these charges, and starting over here at the right side, they're very positive, and then you can see they're getting paler in the middle, so they're less positive. And as we go to the left, they get paler and paler and paler, and finally we have a neutral one, and then they start to get just a little bit negative. So here we've got a gradient of charge, mostly due to positive rings, but a couple negative ones. And so if we just do the calculation and add up the field at a whole bunch of different observation locations inside the wire, we find something that's actually pretty interesting, which is not only is the electric field along the axis, the center line to the left, and uniform in magnitude. So remember, the observation locations are where the tails of all these arrows are. It's actually uniform across the diameter of the entire cylinder. There's actually no variation there. And so the electric field that in the locations we care about, where there are electrons that can be affected by it and move, actually is uniform and points along the wire, which means that electric field would be sufficient to drive a current that wouldn't vary in time or in space along this wire. Now, there are electric fields elsewhere, so that if we show the electric field outside the wire, we see that, of course, there are electric fields due to these charges pointing away from the wire, but we don't care about those because there aren't any electrons there to be affected. So the field we care about is this field inside the wire due to these charged rings. And we see that, again, that a gradient, I'll just get rid of that because it's distracting, but a gradient of charge along the surface of the wire, and remember, all the excess charge has to be on the surface of a conductor, this gradient of charge is sufficient to make a uniform field of the kind we need to drive currents in a circuit. So that's some ammunition for the reasoning we did last time. Okay, so how does this actually work out in circuits? So what I'll show you first is just a really simple circuit. So here's a circuit that looks, again, we're using this idea of a capacitor whose charge doesn't change even when charge flows off of it. So a mechanical battery to run a circuit, and the wire. So here's the capacitor, that's the battery, and then the wire is a wire that has a square cross section because that was just a lot easier to do computationally. And so what this program did was calculate the amount and sign of charge on the surface of the wire in the steady state. Like you start off with some charge distribution and just see how it ends up. So the process we went through in reasoning, except done by a computer. And so what we can show, and so negative charge is blue, positive charge is red. You see, not very surprisingly, there's negative charge near the negative plate, a lot of it, positive charge near the positive plate. But what you also see is there's a gradient of charge. So up here at the top, there's a lot more positive charge, and down here near the bottom, there's very little positive charge, a little bit more on the corners than and a few odd places where there's charge of an odd sign just due to polarization. But here's the thing, if we look at we use these charges to calculate the net electric field inside the wire, and we're going to show it on top of the wire just because you couldn't see it otherwise. So we find inside the wire, the electric field is uniform and it follows the wire due to the charges both on those capacitor plates, our battery, and the charges on the surface of the wire. So the net electric field ends up being completely uniform in this circuit. So which contributes more, the charges on the battery or the charges on the wire? Well, let's show those contributions. So the magenta arrow is the charge. It says external sources, but that's the charges on the battery, the electric field due to the charges on the battery. And the green arrow is the electric field due to charges on the surface of the wire. And we see when we're up here near the battery, they're both super big. But the battery must be winning because the field points to the left, net field points to the left. But as we start to go around the circuit, we find that charges on the surface of the wire, their field represented by the green charges, is actually much more important. And now that we're far enough away from the battery, since it acts like a dipole, that contribution is nearly zero. And down here on this branch of the circuit, the net electric field is almost entirely due to charges on the surface of the wire. And as we come back toward the battery and get closer, it starts to make big contributions. And so if we show the net, we do this, repeat this and show the net field, we can see that these contributions are changing in magnitude and direction, but they always add up to a net electric field that points in the appropriate direction and has the same magnitude. Now we used that snaky circuit as an example because it was really easy to reason about the bends here. And you can see that the surface charge distribution on this circuit is more complicated because different pieces of the circuit are polarizing each other. But when we look, we still get, due to the superposition of the field due to the battery, the magenta arrow, and the field due to the charges on the surface of the wire, we still get an electric field that is uniform, a net electric field inside the wire that's uniform and follows the wire. So that's how that plays out. Okay. So I will put, this program is available in the GlowScript demos. I'll put a link to it in Canvas. And I'll also put a link, I don't have time to show it to you now, but I'll put a link to a video of an experiment in which we show that we can actually detect the charge on the surface of the wire. So how much charge is on the surface of these wires? Typically not a whole lot, because you don't need a very big field, electric field, to actually drive electrons in the sort of simple battery and bulb circuits that we're working with. And in fact, the amount is so little that if you took like a charged tape and tried to see if it would repel your wire, you wouldn't find that it did. But you can run a circuit. What's in that movie is a circuit that has a 10,000 volt power supply as opposed to our 1.5 volt batteries. And there's actually bare wires, and then there are resistors, which are things that need a big electric field to get any current through them. And so these are places where we need big electric fields to get a current through. And So we can actually use a luminized piece of mylar, I think is what we actually use. So something that's very light, or maybe it's a piece of tape with a piece of aluminum foil on the end. And you can see that it actually gets polarized by the charge on the surface of the wire, attracted to the surface of the wire, touches it, charges by contact, and gets repelled. And so you can actually detect that. So I'll put a link to that in Canvas so you can watch it. Okay. So now our question is how we know something about the electric fields that drive current in wires, and we know what charges they're due to, but how can we calculate how much there is? And for that, we're going to use two principles. So we've got the current node rule, which really means we can't use up electrons. And we know that in the steady state, currents are not changing, currents are steady. So therefore, electrons can't be piling up anywhere. So that says the sum of the current into any part of the circuit, number of electrons per second, has to be equal to the sum of the current out of that part of the circuit. And our old friend potential, in the form that the potential difference for a round trip has to be 0. Okay, so those are our, and this really, we'll see, has something to do with energy conservation, actually. And we also need some definitions. So we have, remember, some equations we worked out where the number of electrons per second was equal to NAV, where N was the density of mobile electrons, A is the cross-sectional area, and V average is the drift speed. And V was equal to the mobility times the net electric field. So the electron current was, we could write as NAUE. And conventional current was just Q times I here. And here this is electrons per second, and this is in coulombs per second, or amps. Okay, so let's consider a simple circuit like the one we had in the VPython program, where we have a battery. So this is plus, that's minus. And we have a wire that isn't a terribly good conductor, so we need a reasonable electric field to make currents flow in there. And we're going to call this location A and this location B. Okay, so we know that if we have current flowing here, so we've got electrons flowing that way, that means that we must have an electric field driving this current pointing the other way, and that's consistent with what that's consistent with the polarization of the battery here. And so everywhere in the circuit we would have, as we saw in that VPython program, an electric field that's uniform in magnitude and follows the wire. And that's due not only to the battery, but to the charges on the surface of the wire. And so this is the net field inside the wire. So we could calculate the potential difference VB minus VA, that's just going to give us minus the integral of E dot dl, starting at A and going to B. And there are a lot of different paths we could take to get from A to B. So we could take a path that actually goes through the air. So that's one path. It's not very useful because we have no idea what the electric field there is and we don't care. We could take a path that goes through the wire, and that's an interesting one. And so let's try that. So let's take a path that goes actually. Let's take a path that goes through the wire. So it starts at A, goes around, and it goes to B. So okay, well, this looks like a pretty complicated integral because E is always in a different direction. But actually, DL is always in a different direction too. So both E, the direction of E at any location is different, but also the direction of the path is different. So at this location here, where E is pointing down, we also have a little DL going down too. And over here, when E is to the right, we're actually going to have a little DL to the right. And here, so it turns out in every step we take, this little tiny infinitesimal DL is always parallel to the electric field at that location. And that makes that really, really simple to add up. So we find, because so E dot DL is always the magnitude of E times the length of our step times the cosine of 0 degrees, so 1. And there's a minus sign here. So VB minus VA is just going to be the sum of all these E times minus E times DLs. And so we can write it as, and this is a constant. And if we sum over DL, that's just the length of the wire. So this actually just turns out to be a minus E times the length of the wire. So that was actually a super easy calculation. Okay, well, now if we could also go take a path through the battery, though. So we better get the same answer. And that must mean that there's actually an electric field inside the battery. And it would have to be a different electric field inside the battery because the distance is a lot smaller. So it suggests that so we would guess that there's an electric field pointing from the positive end to the negative end of the battery, so pointing the other direction. And it probably has to be bigger than the electric field in the wire, because if VB minus VA is going to be the same, come out the same, then for a smaller distance, we'd need a bigger field. So I'm going to say this is the electric field in the wire here. So I'm going to write this as E wire times the length of the wire. So path through the battery here, taking that path, we still have E battery is parallel to DL. So we would get VB minus VA is equal to minus the magnitude of the electric field in the battery times the separation of the plates. We'll call it, so this distance here is S. And therefore, if we go all the way around, so we take a path that starts at A, goes all the way around to B, and then back to A, we should get 0. So we find that that the absolute value of these two things has to come out to be the same. The signs are different. So what does it mean to have a potential difference across a battery? Well, for one thing, it's actually a thing that we can measure, and I'm going to try to show you that. Here. So I'm going to stop sharing my screen so I can actually try to show you that we can measure potential differences. So this thing is it's called a multimeter, and it's called a multimeter because it measures a lot of things, and I'm not sure it's possible to get the scales into focus, but it's got 2 wires coming out of it. So one comes out, one's red and one's black. And depending on how you set the dial, it measures different things. So I'm going to set the dial to measure what says volts DC. Okay. And I need a thing to prop this up on so you can see there. And if I just put the 2 leads together and make sure they're touching, it gives me a reading of 0. There's no, what it's measuring is the potential difference between these the ends of these 2 wires here. And it gets a 0 potential difference, saying there's no electric field between them because they're touching each other. So let's see what happens if I ask it to measure the potential difference across a battery. So I'm going to take the red lead and put it on the positive end of the battery. And I'm going to take the black lead and put it on the negative end of the battery. And we see there's a decimal point you probably can't see. But what it says is 1.61 volts. Now this is supposed to be a 1.5 volt battery, so why are we getting 1.61 volts? That's because it isn't exactly 1.5 volts. It depends. The actual potential difference put out by a battery like this depends on the particular chemical reactions going on in the battery. And these alkaline batteries, when they're fresh, typically give you 1.6 volts. Now, what happens if I actually switch the connection? So I put the red lead of the multimeter on the negative end of the battery and the black lead on the positive end, then we get a negative 1.6 volts. Whoops, it's actually kind of hard to keep this contact here, which tells us that that we're going to get a positive reading if this black lead is attached to the negative end, and otherwise we'll get a negative reading. Okay, so these are things we can measure, and we can measure potential differences across wires in circuits as well, and you will do less of that than I would like you to do, but you will at least work with the TAs in lab to do some measurements of this kind, where they'll make measurements for you. Okay, so what is this potential difference across a battery tell us? It tells us there's an electric field there, but it also tells us something about energy in a battery. And so basically what it ends up telling us is how much energy the battery, how much work the battery does per Coulomb, per electron, as it moves charge from the positive, moves electrons from the positive end to the negative end. So if we think about our mechanical battery here, here's our conveyor belt. And what we're doing is we're moving electrons this way. So initially, it wouldn't take any work because there's no field. But as we start to pile up electrons on this plate, and this plate becomes positive, there's actually now going to be a force. There's an electric field inside the battery. So here's our E battery that exerts a force this way on the electron. And we have to, in turning the crank, exert an equal and opposite force. So we need a force by us to keep this going. And they have to be, in principle, if those forces are equal and opposite, then the electrons will move at constant speed, right? And so the force by the battery is the force just due to the electric field, due to the charges on the battery. So we call that sometimes it's called a Coulomb force. And that's just equal to the charge of the electron times the electric field inside the battery. And the force by us is a force, due to something that's not the charges on the battery. So it's often called a non-Coulomb force, and of course, or F in C, and that's going to be equal to minus E battery. Okay. And so the potential difference across the battery is going to be equal to, well, it's this electric field minus the electric field in the battery times the separation of the plates. And that's just equal to the magnitude of this non-Coulomb. Let's do absolute values here, so we don't have to worry about signs. The magnitude of this force by us divided by the charge on an electron, which gives us the electric field in the battery, times S. So this is the energy input per Coulomb. And this has a name. It's called the EMF of the battery. EMF is a really strange term. Whoops, that was not what I intended to do, sorry. It's a really strange term. It's one of these archaic things. It's an abbreviation for the words electromotive force, but it's not a force, it's energy per Coulomb. So, and that's what, so we're just going to call it EMF. And so the energy per Coulomb that a battery puts out. And what a battery does is just maintain this charge this constant charge distribution on the ends of it, so that a current can keep flowing. And when a battery gets used up, then it can't do that anymore, and so it needs to be replaced. So if we just use a round-trip potential difference reasoning on this circuit here, we have to take into account two electric fields, the electric field in the battery and the electric field in the wire. And so if we take a path that goes, I'm not going to draw it inside the wire, but well, I will actually. So we take a path that starts at the positive end of the battery and goes all the way to there. Then we know that delta V round trip is equal to the potential difference across the wire plus the potential difference across the battery. And that's equal to a minus E wire times the length of the wire. And this is equal to the EMF of the battery. And now this is going to be a positive number because our path went from negative to positive. So here, when we're in the wire, our path is in the direction of the wire. When we're inside the battery, our DL is opposite. And so that's a positive number. And we know that this has to be 0. And so, in fact, we can calculate the electric field in the wire, which is where we're getting to. So the magnitude of the electric field in the wire is just equal to the EMF of the battery divided by the length of the wire. And so if the EMF of the battery is 1.5 volts, and the length of the wire is equal to 1 meter, then the electric field in the wire would be 1.5 volts per meter. And this actually, we can write these. So again, this is sometimes called a loop rule when we're talking about circuits, but it isn't specific to circuits, of course. It's always true for fields made by charges. So that, and it applies to any circuit. So that if we had a circuit where we had a wire coming out here, say, and then it was connected to two different wires, one that went that way and a different wire that went that way. There are now several paths we could take. So we could take path 1, and so we'd have, if we call these wires 1, 2, and 3. So path 1 goes through wires 1 and 3. So for path 1, we could write our equation and back to there. So we'd have minus E in wire 1 times the length of wire 1 plus minus E in wire 3 times the length of wire 3 plus the EMF of the battery equals 0. And if we take a path 2, which goes around the outside, so let's make that so this is path 2. So we'd have a minus E1 L1 plus a minus E2 L2 plus the EMF of the battery equals 0. And they're in some sense independent. It has to be true for both paths. And if we combine these equations, some things drop out. So these are the same, and the EMF is the same. And so we find that E3L3 has to equal E2L2. And so there are various kinds of reasoning we can do with this. And it applies to any circuit. So we could have all kinds of things in the circuit. So we could have a light bulb and a capacitor and a wire, and it doesn't matter. So we have 1, 2, 3 wires, and so delta V round trip equals 0 equals minus E1 L1 minus the electric field in the bulb times the length of the filament minus E2 L2 plus whatever the potential difference is across the capacitor. So this is delta V wire 1. This is I'm going to write this as a plus minus here. So that's delta V bulb. That's delta V wire 2. That's delta V capacitor plus EMF, plus wire 3. So we can apply that various ways. Okay, so let's think. For a minute here about some loop equations we could write for different circuits. So here's a circuit where the wires are all made of the same material, but one piece of the wire is actually narrower than the others. So both of these fat wires have cross-sectional area A1 and length L1, and this thin wire has cross-sectional area A2 and length L2. So if we're going to write an energy conservation equation for this, which of these equations would we actually write? Filaments actually burn out due to evaporation. They get hot. They're very, very thin tungsten wires. And they get so hot that some atoms actually start to come off of the filament. And you'll see in a burnt out incandescent light bulb, you'll often see kind of a grayish deposit on the bulb, and that's because the filament actually evaporated. One reason LED lights are good is they last a long time. Okay, let's see what you guys said. Okay, some of you aren't saying anything, but we'll see what you said. Okay, so the majority voted for equation 3, but there are some votes for other things, so it looks like we do need to discuss it. 3 is correct, and 1 is indeed wrong, and the question is, why is answer 1 incorrect? And for this, we have to go back to thinking about the node rule, actually. So since the current in wire 2 has to equal the current in wire 1, then we have NA1 V1, NA2 V2 has to equal NA1 V1. Since this cross-sectional area is small, that means we need a bigger drift speed. And since V2 is the mobility times E2, we're going to need a bigger electric field. So we're going to need a really big electric field in this wire and smaller electric fields in that wire. And that means that we can't use the same symbol for the electric field. Now, we correctly conclude that the electric field in these wires that have these same cross-sectional areas is going to be the same. So in fact, in a path that goes, so our path is clearly going that way. So we're starting at the negative end of the battery since we put that first. So we've got the EMF of the battery, and then we've got this. So we have a plus EMF of the battery because we're going against the electric field in the battery. And then we have, we're going to have a minus E1 L1. So I'm going to write this, I'm going to write plus signs just to make it clear that we're adding potential differences. A minus E1 L1. That's for what this wire on the left here, this wire. And then we have a minus E2 L2 because it's not the same field, it has to be bigger. And now we've got another minus E1 L1, and that equals 0. So we have to do a little thinking about what things we can really lump together and what things might be different when we do them. Okay. So let's consider what we can learn just by using these energy arguments when we can predict. Now, one thing about ordinary circuits, the kind we've been building with, a light bulb and a couple wires, is that in many ways, they're kind of like this circuit, in the sense that to get the same current through something like a light bulb or a narrow wire, you need a big electric field, and other wires connecting it have bigger cross-sectional area or bigger mobility, and they have small electric fields. So in a circuit involving a light bulb, something like this, so here's a connecting wire, here's our light bulb. The light bulb is on. these connecting wires, even though we draw them as being skinny, are actually fairly thick, and they're often made of copper. They're made of something that's a really good conductor. And so, so the potential difference across those wires is not zero, but it's often very small. So delta V of the wires is often negligible compared to the potential difference across the light bulb, because the light bulb needs a really big field to get the electrons to go through the filament, whereas the wires don't need a big field. There's a lot more electrons. They have a much bigger cross-sectional area. And so that it's often reasonable in these cases to say that that although we would write a loop equation as plus the EMF of the battery plus a minus E wire L wire plus a minus E bulb L of the filament plus a minus E wire L wire is zero, that this electric field in the filament is so much bigger that we can often neglect we can approximate these as zero. And you'll see that often done in discussions of circuits. It's not really zero, and even that multimeter I showed you will actually let you measure a potential difference across the wires, but it turns out that it's on the order of millivolts, and this is on the order of, this is close to the potential difference across the battery, the EMF of the battery. So it's a reasonable approximation to make. So let's think about two different circuits here, two simple circuits that just have a battery, some connecting wires, and then a wire that's a poor conductor, so it's a very high resistance. We typically use so it can be something called a nichrome wire. It's not a very good conductor. It's made of nickel and chromium, and it's used when you want exactly that. And so what we're going to do is this distance, we're going to take half the, let's make it look more like half the length of this wire, and compare the current in this circuit. So this is circuit A, to a situation where we use the entire length of the nichrome wire in the circuit. And we'll call this circuit B. Now we're using the same battery. So the question is, how does the current in circuit A compare to circuit B? So let's see what your guess is that it might be. So since the current is going to be determined by the magnitude of the electric field in this wire, okay, so remember that I equals NAUE here. Which statement is going to be correct about these circuits? Let's see if we can get this all on the same page. They're called 1 and 2. This is so which of these statements about these circuits is going to be correct? Here. let's do this. We'll move our diagrams so we can see everything at the same time. That's 1. That's 2. Now we can blow this up a little bit better. Okay, so most of you figured you had to do something with that 3, but you weren't entirely sure what to do with it. A few more people voted for 2. So let's see what the answer, let's see how we can figure this out in a principled way. Okay. So in circuit 1, so here's circuit 1. We're just going to write a loop equation. So here's our loop equation. So we're going to take a loop that starts here and goes back to there. So we have the EMF of the battery plus the potential difference on the wires, which we're going to say is negligible here, plus these connecting wires, these thick connecting wires, plus the electric field. So here's E1. So the potential difference in the nichrome wire, which is minus E1 L over 3, equals 0. So we have EMF equals E1 L over 3, and if we solve for E1, it's equal to 3 times the EMF over the length of the wire. In circuit 2, we have a wire that's got length L, so we've got an EMF plus the potential difference across the wires, which is essentially negligible, plus now we're going to call this electric field E2. So we're going to have a minus E2L equals 0. And so we have EMF equals E2 times L, and that implies that E2 is equal to the EMF over L. And we see that, in fact, we do not get the same electric field in these wires, that in circuit 1, the electric field is actually 3 times greater than it is in circuit 2. And what does that tell us about the current? Well, since the electron current I1 is going to be N A U E1, and the current in circuit 2 is going to be N A U E2, and N and A and U are the same. That's going to be equal to N A U times E1 over 3. So in fact, I1 is going to be 3 times greater than I2. So the battery alone doesn't determine what's going to happen in the circuit. The behavior of the circuit is completely global, and it has to do with, and in order to reason about behavior of circuits, we need to reason about the electric field in the different components of the circuits, and also make sure that we're not losing electrons anywhere. So the same battery can produce different currents under different circumstances. So circuit one in this case has, so we now are comparing circuits in which the wires have the same length but different cross-sectional areas. So here's one. And here's two. So which of these statements is going to be correct? Okay, so the biggest vote is for a factor of 4 here. But let's see if that's right. Let's actually work it out. So here we've got EMF, here's our loop equation, plus I'm going to neglect the wires, a minus E1L equals 0. So E1 equals EMF over L. Here I have EMF plus a minus E2L equals 0. So E2 equals EMF over L. And so the 4 people who actually said that are correct. Now, are the currents the same? No, because a bigger cross-sectional area means a bigger current. So I2 is not equal to I1. In fact, I2 is going to be greater than I1. But E2 equals E1 because it only depends on the length of the wire. So what do you need in chat? What do you need to think about out of what we've done today?